Good morning, everyone. This is the Nicolet lecture. There will be a couple fairly quick introductions of our Nicolet lecturer, who is Charles Barth from the Laboratory for Atmospheric and Space Physics. Just a word before I introduce the next introducer. I'm quite happy to be able to preside over the session. I myself was a postdoc, at least a couple decades ago, at the Laboratory for Atmospheric and Space Science, and was introduced into the world of nitric oxide. And it's I think a fraternity from which you can never escape, I think. Yeah? The molecule's always with you. Our next introducer is going to be the president of the Space Physics and Astronomy section, who's going to make a presentation. That is Dr. Tim Killeen, who will in turn introduce Professor Baker.
Good morning. This is one of the Bowie lectureship presentations that the AGU gives, named after the first president of the American Geophysical Union, Professor Bowie. And our section, SPA, Space Physics and Astronomy, has three named lecturers that it gives over the years on an 18-month basis. These represent the highest award that the section can give to any individual for distinguished contributions in our field. The process is one that has open nominations and then selection by an executive committee. It takes several months to do. And we're very honored this time that we have one of our most distinguished colleagues who is going to receive the 1999 Marcel Nicolet Award and give us a lecture on that. I'd like to make a plug for the next cycle, which is going to be the Van Allen Lectureship, which will be given in the spring. Nominations are open for that right now, so please contact any member of the SPA Executive Committee if you have anybody in mind for that award. But I'd like to ask Professor Barth to come forward and receive his certificate from the, excuse me for that, which says that the Space Physics and Astronomy section recognizes Charles A. Barth, the 1999 Marcel Nicolet lecturer, for his talk, How the Sun Controls Nitric Oxide in the Thermosphere. I'd like to congratulate Charles. And for the real introduction, we're gonna ask Dan Baker, who's a close colleague of Professor Barth, to give you some background.
It is indeed my honor and distinct privilege to be able to introduce this year's speaker in the Nicolet Lecture Series. Professor Charles Barth has had a long and highly distinguished record of achievement in theoretical and experimental exploration of the Earth's atmosphere, as well as a remarkable record of planetary exploration. Professor Barth got his Bachelor of Science degree in 1951 at Lehigh University. He went on to earn a master's degree in 1955 and a PhD degree in 1958, both of his advanced degrees being obtained at UCLA under Joseph Kaplan. Dr. Barth's graduate work was done in laboratory studies of emission spectra of oxygen molecules with an eye toward explaining night air glow. In 1958, Dr. Barth went to Caltech's Jet Propulsion Laboratory. Mind you, this is even before there was a NASA. His initial work at JPL was looking at ways to freeze atoms so the frozen material could be used as rocket fuel. However, rather quickly, Dr. Barth became very active in the study of atomic reactions in the upper atmosphere and the ultraviolet observations of such reactions. In 1961, he wrote a chapter in a book which addressed most of the key reactions of atomic nitrogen and oxygen for the upper atmosphere. Dr. Barth considered the differential equations describing reaction rates, and he did numerical integrations on the then impressive IBM 7090 digital computer. His work gave theoretical predictions of the altitude distributions of the densities of nitric oxide, NO2, and ozone, and showed the expected lifetime of these key molecules in the atmosphere. This initial theoretical work began a lifelong fascination with nitric oxide and its role in atmospheric chemistry. In 1965, Dr. Barth took two moving vans full of equipment from JPL, I'm sure with official permission, and moved to the University of Colorado in Boulder. He took over the directorship of the Laboratory for Atmospheric and Space Physics from Professor Bill Rentz, and he took a professorship in the Department of Astrogeophysics. A new building was built on the CU campus in 1965 to house the newly energized LASP, and a remarkable epoch in space exploration began. LASP had in 1956 spun off the group that founded Ball Aerospace, and they were doing precision pointing devices for sounding rockets. Professor Barth began using sounding rockets even while still at JPL to study nitric oxide in situ within the upper atmosphere. His 1966 paper on the subject, by the way, showed about 3 orders of magnitude disagreement between his observations and his 1961 modeling results. I believe that he has since that time leaned heavily toward the experimental side, but he also confirmed did more theoretical work to explain the discrepancy. However, like Sir Arthur Eddington, Professor Barth has tended to believe an observation only when it's confirmed by theory. Beginning at JPL and throughout his career at Colorado, Professor Barth has very successfully commingled his work on Earth's upper atmosphere with an aggressive and richly rewarding planetary exploration program. He was principal investigator of experiments on Mariner 5 to Venus, Mariner 6, 7, and 9 to Mars, and he's been a lead co-investigator on Pioneer Venus Orbiter and the highly successful Galileo and now Cassini missions to the outer planets. He has been PI for more than 50 rocket experiments in Earth's atmosphere, for OGO 2, 4, 5, and 6 spacecraft missions in Earth orbit, and for Apollo 17 and space shuttle investigations. In many ways, the most notable and remarkable achievements in Professor Barth's career have been his development of scientific satellite programs within the university laboratory setting. In 1979, he was selected as PI for the Solar Mesosphere Explorer, or SME program. SME operated magnificently from 1981 to 1989. It turned countless students into valuable scientists and engineers, and returned outstanding data on the solar ultraviolet spectrum and the variations of ozone and nitric oxide in Earth's mesosphere and thermosphere. When I came to LASP as director in 1994, Dr. Barth and his team were actively and enthusiastically on the hunt for a new small satellite program under USRA's Student Demonstration Initiative. Dr. Barth was proposing to build, test, and operate a complete spacecraft, but this time it would be accomplished with a very high proportion of the work being done by students, and the overall budget was only allowed to be $4 million. USRA very wisely chose Dr. Barth to lead the first STEADY mission, which was dubbed SNOE, the Student Nitric Oxide Explorer. I'm convinced that only Charles Barth could have really pulled this off. Excuse me. But pull it off he did. SNOE was successfully launched in February 1998 and has worked superbly well since that time. Excuse me. On a more personal note, I want to conclude my introduction by expressing my admiration and immense respect for Charles Barth. I believe he has built one of the finest university space research laboratories in the world, and it has been my privilege to step in behind him to direct this wonderful organization. Charles has very large shoes to fill, but he's been very generous and very supportive of me as I've tried. He and I have been working closely together on analysis of SNOE, SAMPEX, and ISTP data, and I've learned a great deal. Charles Barth has accomplished an amazing amount. He has educated numerous graduate students, countless undergraduate, and has truly shown what a university can and should be. So I give you Professor Charles Barth delivering the 1999 Nicolet Lecture on how the sun controls nitric oxide in the thermosphere.
Well, thank you for that very nice introduction. And I thank the Executive Committee and the members of the section for inviting me to give this talk. I'm especially pleased because the talk is called the Nicolet Lecture. And what's important is it was Marcel Nicolet that introduced the subject of nitric oxide to us all. And so we'll start. So it was in 1945 that Nicolet, in trying to understand the ionization that was taking place in the D region of the ionosphere, around 80 kilometers, that he knew that ionizing radiation had to penetrate that deeply. And as you know, most of the radiation is stopped above 100 kilometers. He knew there had to be something there that could be readily ionized. And so he recognized that nitric oxide had the lowest ionization potential of the potential constituents. He knew that the sun must be putting out Lyman alpha radiation, remember 1945. And so he decided that there had to be nitric oxide there in order to explain the ionization in the D region. So this illustrates one of the properties of nitric oxide, namely that it does have the lowest ionization potential of the major constituents. What that means is that the ionization that takes place in the atmosphere eventually through charge exchange and dissociative charge exchange reactions, ion molecule reactions, that ionization, much of it ends up in the nitric oxide ion, which then ends up supplying nitrogen atoms. We'll talk more about this. Okay, so here's Marcel Nicolet introducing nitric oxide. Let me tell you about my talk. I'm going to tell you things that make nitric oxide important to understanding the thermosphere. This is one of them, namely the lowest ionization potential. I'm then going to tell you about how nitric oxide is produced in the thermosphere. Then we'll deal with how does the sun control it. And it's going to be in two parts. One part has to do with the electromagnetic radiation that comes from the sun. That controls the region mostly in the tropics. And then we'll talk about the charged particles coming down from the magnetosphere. The sun controlling the magnetosphere then dumping the energy into the auroral region of the atmosphere. And then we'll show you what further importance nitric oxide has in our study of the thermosphere-magnetosphere interaction. So another important property of nitric oxide is its chemical reactivity. So nitric oxide is odd nitrogen. Nitrogen, of course, is even. Oxygen is even. Ozone is odd oxygen. And odd nitrogen reacts with odd oxygen. That means when the two are together in the same location, nitric oxide will cause ozone, anatomic oxygen, to catalytically recombine. The NO will catalytically destroy the ozone. I'm still working on my left and right. So that led to the idea, and in fact it was Susan Solomon, Paul Crutzen, and Ray Roble that put it in this particular form, that during the polar night, when the lifetime of nitric oxide is very, very long, that there is a strong downwelling of the atmosphere in the winter hemisphere, and that downwelling would carry nitric oxide with its very, very long lifetime down through the mesosphere into the stratosphere, where it may react with the ozone, and that has now been shown convincingly to be correct through this data that I obtained from David Siskin using HALOE observations. HALOE observations taken over a 5-year period of the southern hemisphere in the winter, of the northern hemisphere in the winter, showing contours of nitric oxide, and you see them turning downward as they're approaching the polar night. Here in the south, there in the north, and so it's easy, just looking at these contours, it's easy to see how the nitric oxide has its opportunity to move down into the nighttime mesosphere, and perhaps even down into the stratosphere. We should know two things before charging forward. One is that this is a 5-year average, so it takes a long time to collect this very nice latitude survey of nitric oxide using the occultation technique of HALOE. And the other thing, of course, it tells us is we wish we had some observations in this dark region to see exactly what the nitric oxide is doing. So that's a reason now to understand nitric oxide in the thermosphere, because in this example, you're seeing it as an apparent source for the nitric oxide moving downward into the mesosphere. Okay, so we'll now quickly go through the business of how do we make it. And we'll start over here with the major constituents: nitrogen, atomic oxygen, molecular oxygen. We have the two cases, namely the photons coming from the sun, and in particular, what's important for nitric oxide are the energetic photons, namely the solar soft X-rays, 2 to 7 nanometers, 20 to 70 angstroms. So these energetic photons ionize the major constituents, produce the ions. The ions then, as I remarked before, through reactions of various sorts, end up making NO+. The NO+ over here, when it undergoes dissociative recombination, makes nitrogen atoms, the N-double-D with electronic energy, extra electronic energy, and the N-quartet S, many of them with excess translational energy. These electrons also have a chance to directly dissociate N2. All of these things making nitrogen atoms. Nitrogen atoms then react with O2. The N-double-D already has the extra energy, and this reaction goes nicely. Those nitrogen atoms, those ground states with extra kinetic energy, also produce nitric oxide. So here's the source of nitric oxide. Then the loss comes from the photodissociation, producing a ground state atom, this time a cold ground state atom, which then does not have much of a chance to make more nitric oxide, but does when it reacts with nitric oxide, it destroys it. So this is the destruction mechanism. Now this is important. That's down around 191 nanometers. This is important because here's the lifetime. That's the photodissociation rate, the lifetime. So this says that the nitric oxide will hang around for a little more than a day. But that's at the subsolar point. So in the equatorial region, with the Earth, of course, rotating, that sort of averages out to about 2.5 days. But up in the auroral region, with the larger solar zenith angle, the lifetime really averages out to about 5 days. And so this leads to this long lifetime of nitric oxide as we proceed toward the poles. Okay, so those are the ideas. Two sources. I'm backing up. Two sources, namely the solar soft X-rays, the HNU, but then also in the auroral region, the precipitating electrons, the 4 keV electrons that are coming in, doing the ionizing, producing secondary electrons. So we have those two sources. Here's a model, photochemical model, all by itself, only with the solar soft X-rays. It's at the spring equinox, and so the two hemispheres are being equally illuminated. The maximum, this is a prediction, a model calculation, the maximum that's calculated should occur around 110 kilometers right over the equator. It drops off going to lower altitudes because the solar soft X-rays are absorbed more rapidly than the NO is photodissociated. It drops off in going to higher latitudes because of the increasing solar zenith angle. And so here's the shape then that you would expect only from solar soft X-rays. Now here, in this model, this is a tutorial. What we've done is just to add in at 2 latitudes, around 65 degrees north and south, we've added in the auroral component. So here come the 4 keV electrons, and we're doing it here just in this latitude band. And you see it's producing nitric oxide, also right around 100, 110, maybe on our scale, 106 kilometers. And so the auroral source should look like this. The soft X-ray source should look like this. And what the data looks like, now this is an observation from the SNOE spacecraft, taken in 1998 at the spring solstice on a sort of an ordinary day when there's a little bit of auroral activity. Here is nitric oxide in the tropics. Its maximum is around 110 kilometers. But here's that larger amount in the auroral zone in both hemispheres, and in this case, both hemispheres are being illuminated approximately equally. Okay, so now the first story we're going to tell is what happens when we take the amount of nitric oxide right here near the equator in the tropics, plus or minus 20, 25 degrees, right around 110 kilometers. And we plot it out over a whole year. So here's a whole year of SNOE data. SNOE is a polar orbiting spacecraft. It's in a sun-synchronous orbit, so it's always measuring at the same local time, which is about 10:30. This is a 10:30 a.m. Observation. 15 orbits a day. What we're showing over here, then, for each point, that's the average of this latitude, altitude region here for a whole day, for all 15 orbits. So the first thing you see is that there are variations. And so the variations, with our ideas about the solar soft X-rays producing the nitric oxide, we then look for variations in the solar soft X-rays. So here are the solar soft X-rays. This is labeled 2 to 10 nanometers with the soft X-rays during the same time period from the spring equinox for a whole year, solar soft X-rays moving up and down. And even from where you're sitting, you can tell, yes, this looks like a 27-day variation, and that looks like a 27-day variation. And so if we plot one against the other, we see a very, very nice distribution of the nitric oxide then being dependent on the intensity of the solar soft X-rays. Okay, here's a straight line being fit to the data. Has a nice correlation coefficient, 0.8. And so we take this to confirm the idea that it is the solar soft X-rays that are controlling the variation in the amount of nitric oxide in the thermosphere in the tropics. Okay, but now we notice if we extrapolate the straight line down to 0 X-rays that there's a finite amount of nitric oxide. And so now we still have the question of where is this other source of nitric oxide? Where does it come from? Ray Roble has modeled the thermosphere, and in the time GCM coupled it in fact with the mesosphere and below. The first thing we'll put up our data again. First thing you note is that the general characteristics of this model and of the data are about the same. That here's the production from the auroral electrons. Here's the production from the solar soft X-ray. Same characteristics. Now we're trying to think where might we get extra nitric oxide that does not vary long time constant. Where might we get it in this region here? So one idea would be, well, since there's more nitric oxide in the auroral region, maybe it's transported from the auroral region down into the tropics. This seems like a reasonable idea. When Ray Robel, though, has treated that in his model, taking into account in great detail the winds that occur, it turns out that the meridional winds at 105, 110 kilometers are very, very slow. And so maybe those winds are not enough to move the nitric oxide to the tropics. However, I think it's still an idea that we should continue to explore, as well as maybe other ideas as to what could be producing a small but constant amount of nitric oxide in this region. If you want to think about that, the amount here we go. The amount would be about, if you imagine, what would it take to get 2 times 10 to the 7th, 2 times 10 to the 7th molecules per cubic centimeter. It would take about 0.1 ergs per square centimeter per second. Okay, we're now ready for another topic. But first, we're going to summarize what I just said. So in the tropics, it's the solar soft X-rays. And specifically, the most important are those in the 2 to 7 nanometer region, which get down to about 110 kilometers, where they do that photoionization. The photoelectrons that are produced produce additional ions, and all the ions end up producing excited atoms, which react with the molecular oxygen to get the nitric oxide. So now we're going to begin to tell the story of what happens in the auroral zone. So I'm going to show a sequence of observations starting May 2nd, 1998. May 2nd, 1998. And here's nitric oxide being produced in the south from auroral electrons in the north. And notice there's more in the south than in the north. I'm going to run through a sequence of several days. Still looking at the right, you see that on May 3rd, that the nitric oxide density has increased. On May 4th, it's increased again. And in fact, here's the highest point we're going to show you, right there in the south. So this is in a geomagnetic storm, May 4th. That's a large storm that occurred in 1998. You notice from the previous day that not only has the density of nitric oxide increased, it's moved to lower altitude, meaning more energetic electrons, and it's moved equatorward. And once more, you see that there's more in the south than in the north. Okay, the storm is over. It's beginning to decrease, and you see the nitric oxide slowly now dropping off. This is demonstrating our idea that the time constant is 3 to 5 days. Time constant for nitric oxide in the polar regions, in the auroral regions, 3 to 5 days. It's slowly going away. Now here's another plot over here where this is a slice. We're now going to show us here on the left. We'll show a slice through the thermosphere right at 106 kilometers, right through here, for every day for a 1-year period, starting in the spring of 1998 to the spring of 99. The large storm that I just showed in May is right here. So in this representation, then here's the idea that the nitric oxide, first of all, in the south is greater than in the north. That when it increases, it moves equatorward. When it decreases, it then retreats back. And so now we need to start to think about how come there's a hemispherical asymmetry. So now, if you look at this whole time latitude diagram, you see during this season here that it does look like there's more nitric oxide in the south than in the north. But notice in the same season, but in the north, this of course is spring in the south, spring in the north, and we're looking in the south. When we look at fall in the north, we see that there's more nitric oxide there than in the south. So this looks like the hemispherical asymmetry is seasonal. That's the last day of that previous event. And so what we're going to do now is we're going to look at this event right here, day 318, fall in the north, and you see, in fact, there is more nitric oxide in the north than in the south. And as we carry it through that storm, you see that same characteristic of the nitric oxide increasing and then decreasing with a slow time constant all the time, with there being more in the north than in the south. So what are the ideas and what produces the hemispherical asymmetry? So here's the review of fall in the south, greater in the south than the north, fall in the north, greater in the north. Okay, so it may be the result of what we call seasonal changes, what you and I daily call seasonal changes, based on the obliquity of the Earth as it moves around the sun, and that means that the orientation of the Earth's magnetic field with respect to the solar wind changes throughout the year. Also, as you well know, since the Earth's magnetic field is offset from the geographic pole, that in fact, during a daily rotation, that orientation changes. And so there's a constantly changing between the orientation of the magnetosphere and the solar wind. And with the seasonal one, you can imagine how that geometry then may end up causing more in the one hemisphere than in the other hemisphere, depending on the season. Now, during this particular magnetic storm that we investigated, from observations from the SAMPEC satellite, that we did find out that there was more precipitating electron flux in the south than in the north. And so here we did have the example of more electrons, more nitric oxide, less electrons, less nitric oxide. So here then is our summary for how the sun controls nitric oxide in the auroral region. So first of all, it's clear it's the precipitating electrons that are the cause. And the precipitating electrons are variable, therefore the nitric oxide is variable. And it's the sun producing variations in the density and velocity of the solar wind that's interacting with the magnetosphere, which is ending up causing the magnetosphere then to have a varying precipitation of electrons into the auroral region. It's the roughly 1 to 10 keV precipitating electrons. In many of the examples that we're using in the models, it's around 4 keV. They get down to the 100 to 110 level of the thermosphere where they ionize each of the major constituents. Remember, getting those secondary electrons, the secondary electrons get additional ionization. All these ions end up producing excited nitrogen atoms, which then produce nitric oxide. Okay, this is a time to remind us of another property of nitric oxide, namely that it has a electric dipole moment. It's a heteronuclear molecule, so it does have a permanent electric dipole moment. Remember that molecular nitrogen, molecular oxygen, both homonuclear molecules, do not have electric dipole moments. Therefore, they do not radiate in the infrared. Nitric oxide does radiate in the infrared. It radiates in the 5.33 micrometer band of nitric oxide, cooling the atmosphere. So when there are large amounts of nitric oxide produced, particularly in the auroral region, the nitric oxide then has a chance to help cool the atmosphere. You remember the atomic oxygen, of course, does do some radiating, but that's at higher altitude. And at lower altitudes, of course, it's the CO2 that cools the atmosphere. So there's another property of nitric oxide. So here's our summary of the behavior of nitric oxide, namely that it's variable. It varies with time, latitude, longitude. Processes that produce nitric oxide, the solar X-rays, the precipitating electrons, they vary. Now they have time constants, now what to think about, they have time constants of minutes or seconds. They certainly vary from day to day. The processes that destroy nitric oxide have a time constant of 3 to 5 days. See, so we have something coming in that's varying rapidly, but the destruction process is a longer time constant. What this means is that the thermosphere, the nitric oxide in the thermosphere, has a record. Its density is a record of the amount of energy that has come into the thermosphere during the previous day or 2 or 3. It's doing the integrating. There's that idea. And here's the next idea, which is namely that the nitric oxide may be used as an indicator of the amount of energy input into that lower thermosphere. So here's the data now in a global display. This is May 2nd. It's that same geomagnetic storm that I showed you before. And now you notice, in addition to that variation with time and latitude and altitude that we saw earlier, there is also clearly a variation in longitude. So here's nitric. Remember, the SNOE spacecraft is making 15 orbits a day, making 15 observations every day, doing a map of the nitric oxide. And so it's measuring here on this relatively quiet day at the beginning of a storm. It's showing nitric oxide in the north around here, but with much lower amounts over here in the east. Once again, you see in the south that there's more nitric oxide, but again, you see that the distribution varies with longitude. And so auroral images, auroral global images, and as you know, there's a session today and this, both this morning and this afternoon on global images of the thermosphere. And those imagers, working either in the visible or the ultraviolet or in the X-rays, they show the instantaneous energy input into the thermosphere. If you see a picture of an aurora, that's something that happens right away. The electrons come in, the light comes out right away, and it varies. And we know that from personal experience, from seeing how aurora vary. We know it from the images that you've seen taken from space. The nitric oxide, though, see, it's been sitting there integrating over the whole day. So it has, so this is an image, to repeat myself, of the amount of energy over a whole day. That means if we're going to compare these images, the nitric oxide images, with auroral images taken from the visible, ultraviolet, or X-ray imagers, these images need to be integrated over a period of a whole day to get the total amount of energy going in to the atmosphere over the whole day. Okay, so now what we'll look at is a series, a sequence of images over here on the right during this magnetic storm. And once again, what you should look for is the changing intensity, the changing longitudinal distribution here. So here we saw the nitric oxide increasing a large amount in the south. Here it is in the north, a lesser amount. And you notice as we go through each day that first it grew and now it's beginning to decrease. And notice that the nitric oxide here is at the same longitude it was on the previous day. So it's remembering what happened the previous day. And now you see it decreasing. Okay, and we're going to run through that again. So here's this representation again, and remember I'm showing this storm right here. This is at 106 kilometers, function of latitude. This is at 106 kilometers, where you can clearly see the function of longitude. And the story then that we're telling is that this is the nitric oxide here then is increasing with time because of the varying input of energy from the auroral electrons. It has a distinctive longitudinal pattern which remains in place for several days. Additional implications are that obviously there are not strong zonal winds that are transporting the nitric oxide around in these polar regions, smoothing it out over all longitudes. So we're seeing in longitude, we're seeing the location of where the auroral electrons went in. Okay, and I think we'll end up looking at this one. And over here, now we'll say, what has this got to do with atmospheric models? I showed you the time GCM earlier. That's where Ray Roble takes all of the energy inputs that are available to him and calculates what the nitric oxide, among other things, calculates the density, the temperature, the wind structure, calculates what the nitric oxide distribution should be. In any model, though, of that sort, it's a burden to put in great detail all of that varying amount of energy input. And so usually what's used then are daily averages or some modification of daily averages. And to some varying degree, maybe the same amount of energy is put into the north and to the south, or maybe there is some modification of that to properly take into account the auroral oval in both hemispheres. So what I'd like to propose that we think about the inverse problem. Thinking that the same physical process that produces the nitric oxide also heats the atmosphere. Namely, it's that ionization from the precipitating auroral electrons. Okay, here come the precipitating electrons. They make those secondary electrons. They produce a visible aurora. They produce nitric oxide, and they also produce heat. And heat, of course, changes the structure of the atmosphere. So why not take the nitric oxide global images to deduce the energy input into the thermosphere, remembering it has a time constant of a day or longer. So then these deduced energies, they retain all that spatial information. So they're retaining the longitudinal distribution. And imagine using that as an input to atmospheric models, from which then the output, of course, would be the temperature structure the winds. Okay, I'm going to pursue that idea more, and we're going to do it with a video display. And we're going to warm up the video machine here. And what we'll be showing are images of this type. What we're first going to show are images of this type. And do you want to start it? Yeah. So we're going to run these in movie fashion, and what you're to get out of this is that it's a dynamic phenomena, that it's changing rapidly. We'll run it again as we repeat these. Look first at one hemisphere, then look at the other hemisphere. And we'll repeat it a third time. So imagine, everyone has their own cup of tea. This is the 0 longitude. So the geomagnetic pole is in this position right here. And if we do it, let's do it one more time. And so in the north, you can see the auroral oval here. And again, I would like you to think of that as an image of the energy input into the atmosphere. And now we'll show it in the with a polar view, if we could. Yeah. So here we are. We're now looking on day 121. That's May 1st. That's the beginning of a geomagnetic storm. Longitude 0 is still right here. Longitude 90 west, off in this direction. On this day, very, very clearly, there's more nitric oxide, more energy going into the south than into the north. Okay, the next day, 122, we're beginning to see the development of the storm here in the north. Here it is in the south, and of course, on this side of the projection is the international date line, so there's a time discontinuity here. Remember how the satellite works. It first observes here, and then here, and here, and here, and here. It takes 24 hours to move around to this point here again. So up here, that would be from here, from here around to here. Okay, day 123. Here's the storm coming in now, showing up most strongly here in the southern hemisphere. Here's the auroral oval in the north, and the day 124, right at the peak of the storm. Here's the auroral oval in the north. Remember, the geomagnetic pole is right about there. Auroral oval in the south, geomagnetic pole over here. And now day 125, 126, 127, 128, and you see an expansion, and then let's do one more, 130, and now it's retreating. So what I'd like to do then on both screens is move back to day 125. Day 125. Let's go to day 126. And so I'd like to leave you then with this. Here's an image of nitric oxide in the thermosphere. Here's a polar view on the left. Imagine that it's the integrated result of energy pouring into the thermosphere. There's the record. In the beginning of the talk, I mentioned how nitric oxide in the thermosphere during polar night has the opportunity to be transported downward into the mesosphere. So here's a map of the nitric oxide. I mentioned that the integrated nitric oxide is a measure of the energy that's gone in, and I'm suggesting using that information as a potential input to atmospheric models to then calculate temperature, structure, winds in the atmosphere. Thank you.